So what we are going to do, starting from today's lecture onwards, is we have done a lot of hands-on till now. So now we'll take a shift and we'll start discussing some theoretical concepts about networks. But again, please note that the theory we are going to discuss is not very technical. So it is something which even you think about in your common terms, and what happens in your daily life, you can think about it very easily. So everything we'll discuss, most of it will be intuitive and logical, like most of your other subjects in computer science. And you might even already guess most of the things I'm going to tell you. So I request you to listen to me carefully and try to answer the questions. So just try to answer. Don't worry if your answers go wrong. That's the way we learn. So before starting with anything, tell me how many of you took time to load the GML file I sent you? Did you visualize that network, or did you try to see something else with the network, or did it give you a problem when you were importing it? So if you have tried visualizing it, type yes in the chat window. Otherwise, type a no in the chat window. And type exactly one of these. Navneet and Satvik, you guys joined late. It has been 5 minutes till the lecture started. Now it is becoming a habit from your side. So please ensure that from next time onwards, all of you join the class latest by 3:36. If someone joins after that, I won't give you attendance. So Harshit has tried. Has anybody else tried? I'll keep Shagufta out of it because she's a second year student. She's taking this course out of choice. So Vamshi, Navneet and Satvik. Okay. So Navneet, can you show us the network which you visualized? Can any of you share your screen and show me the network? Okay, so Satvik has shared his screen. You can see the network here. Okay, so what Satvik has done, he has imported this DML file and he's showing us the network here. Okay, and what we see here are the node labels or indices. I think these are the node labels, right? Because we see node 420, which was created by one of you, and these labels, they are not consecutive, right? So these are not the indices, these are the labels. So Harshit pointed out a problem with this here. The problem is we actually are getting some nodes here without any labels. Furthermore, we didn't have these many characters in the file which we created. Our number of characters were less. We had, I think, how many? 34 is it, Harshit?
10 notes, ma'am. 10 notes are extra.
10 nodes. So we have 10 nodes extra. Okay. And how many characters were there in total?
How many characters?
Characters means character names which we created.
There are no names, ma'am, exactly. I think I'll share my
Uh,
screen, ma'am, to show exactly what.
okay, so okay. So what happened? It was actually a problem from my side. There were certain nodes in the GML file which were extra. This happened because I didn't take care of those commas while importing my data set in Network X. So what we can simply do here is we can delete these nodes which do not have any label. So you'll come to know if node is a dummy node by looking at it. It won't have any character name or a label or a gender or remarks. It won't have all those attributes. So we can simply chuck off those nodes from the network. Harshit, have you done that?
No, ma'am, no, ma'am. I'm doing it.
Okay, so can all of you quickly do this? If your Jupyter notebook is up, you just simply need to type a g dot delete underscore vertices and in the argument pass it a list. and in that list pass the indices of those vertices which do not have all those attributes associated with them. So I think that indices are, I can actually type it in the chat window, 5, 28, and then 31 onwards. Do this. If possible, try to show the different genders in different colors and then show the graph to me.
Ma'am, I think it is 3, ma'am, not 5.
Check it out, okay? It might be 3. You can correct me here in the chat window.
Yes, ma'am. Ma'am, here you can see, ma'am.
Hmm. No, no. What you are actually looking at is, I think it's the adjacency list which you are looking at. Can you open the GML file, Harshit?
Okay, ma'am. Okay,
On your
ma'am.
system, just open it in Notepad. I'll show you.
1 second, ma'am. Ma'am.
Okay. So see here. So with ID 0, we have all the attributes. With ID 1, we again have all the attributes. Come down. So ID 3, we have Joy. So he has all the attributes. So what is happening? He actually hasn't recommended any friend probably. Look at this node having ID 5 here. It has a label 8, but it doesn't have any character name, gender, hobbies, age, or remarks. This means that it was a dummy node which was created because of some comma in the file.
Yes, ma'am. Got it.
Right, so delete all the nodes which do not have these attributes associated with them.
Okay, ma'am. Got it.
So use this function zero delete underscore vertices and pass it a list having all those node IDs. Do this, and any of you can share your screen with me once you are done. Any of you close to finishing it, or if it will take time, let me know. I'll just proceed. Okay, so whose screen this is? Satvik. Okay. So Satvik shows us the graph here. All the males are in red color, females are in green color. Then I think these are the node labels which are appearing at a slight distance from the node. Okay, so this is the graph we have. Uh, we can also set the labels to be the character name. So all of you can do that at your end. That's fine. Okay. So we see the graph here. So the question which we posed the last class was, what all would you now want to study from such a graph? Let's say I give you a graph in GML format. So this is a small graph which Satvik showed us, a graph on, let's say, I think some 30 nodes. What if this GML file had a graph of 4,000 nodes? And let's say even not even 4,000, let's say some 100,000 nodes. You can't even visualize the graph because it will take a lot of time to lay out this graph on your screen. In that case, so now assume this, that you have a graph of 100,000 vertices given to you as a GML file. You can assume it to be a social network for now. So the question here is, what all would you want to see in this graph? You can unmute yourself and speak or type in the chat window. So start with the very basic things. Let's say you don't even know the number of vertices in the graph. It's just something given to you as a GML file. You know that this something is a graph, in fact, a very big graph. You have now loaded it in a variable called G. Now, what all would you want to see in this G here? Take your time, think about it. You can type whatever comes to your mind in the chat window. No one? So the very first thing I would want to look at is how many nodes are there in this graph, right? So if I have a graph, okay, Satvik says attributes and degree of each node. Very good answer. So I want to probably look at attributes, maybe how many of these nodes are males, how many of these are females, what is the ratio, and maybe the degree of each node, how many friends does every person has. Okay, any other thing? So we'll take a note of all these and we'll discuss them one by one. So we got two things here, attributes and second is the degree. Tell me something more. Think of something, meanwhile I'll share my screen. Okay, Navneet says neighboring nodes and edges. Again, a good point. I might want to look at which are the neighbors in my node, and yes, he told me maybe the edges in this graph. And if we talk about edges, the very first thing which will come to us is the number of those edges. So these are the first two properties. I might want to look at the number of nodes and number of edges. So that is the first thing we study for any network, be it even your any general network in your graph theory class. Just give me a moment. Just give me a moment. Meanwhile, think of a few other things which comes to your mind. Okay. Let's now talk about a few other things we might be interested to look in. So first was the number of nodes and number of edges. Now look at the third thing which is generally studied is the density of a graph. I'm showing you two graphs, one on the left and other on the right. Which one do you think is denser? By just looking at these graphs, which one of these is denser? The right one. Yes, okay. So by looking at the graphs, I can tell you, yes, the left graph is sparser, the right one is denser. But how do you exactly capture that density? How do you quantify it? So for every measure, which we are now going to see for every graph, we'll figure out a formula which could capture that particular measure. So I want you to come up with a formula which, let's say this graph here is G1, this graph here is G2. So f of G1 should give me some value, some numeric value. And again, f of G2 should give me some numeric value. And these values should imply that the density of the graph on the left side is lesser than that of the right hand side. So this value here should be less, this value here should be more. So what formula can we use? Okay, I got an answer, average degree. Let's see. Okay, any other guesses? Okay, or maybe the number of edges. Okay, let's say we choose the number of edges. I'll get back on the average degree back to you. So right now we are starting to think in very, very simple terms. Okay, maybe the number of edges. What's the issue here with the number of edges? Assume that we choose here. Definitely the graph on the right hand side has a greater number of edges. So it turns out having a higher density here. Now the comparison here, these two graphs which we are comparing here, both of them have actually 6 vertices. What if the graphs which I am comparing here, they have different number of vertices? Let's say I'm saying that I'm going to take the number of edges here, and now let's say I change my first graph, something like this. So I'm going to extend this graph and add a few nodes and a few edges here. And let's say I add some 2000 edges in this fashion, how I am doing it. Now tell me which graph is denser? Still the graph on the right hand side is denser, right? The one on the left hand side is still sparse. But the one on the left hand side ends up having a greater number of edges. So number of edges is actually the right way to go about it, but what we need to do is, uh, okay, Shagusta says average number of edges per node. Uh, Average number of edges per node, is that same as average degree, is it? What we are going to do is we just have to normalize this number of edges here with something. So I need to put something in denominator so that I can compute it over graphs of different graphs having different number of nodes. So number of edges is the right way to go about it in case where the graphs you are comparing have the same number of vertices. So definitely if I'm looking at two graphs, both of which are having 100 vertices, the one which is going to have more number of edges is going to be more denser. So what I'm going to do is I'm going to divide this number of edges in a graph by the total possible number of edges. So this gives me the density. So it simply tells me out of the total edges which are possible in your graph, what fraction of them actually exist. So if you look at this graph here, which we have extended, how many vertices this extended graph now has? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, around 19 vertices it has. If you have a graph on 19 vertices, how many total possible edges can be there? We are talking about an undirected graph here. 19 choose 2, right? Yes. Yes, Ali. 19 choose 2. So that's the correct answer. And what will go in the numerator? How many edges are there? So you can calculate. I think there are around some roughly 12 or 13 edges in this graph here. And if we talk about this graph, how many total possible edges? 6 choose 2, which is what, 6 into 5 uh, by 2, which is 15. And out of this 15, this is not being multiplied, this is 15 here. And out of these 15, how many are actually there? 1 2 3 4 5 6 7 8, I think around 9 or 10 are there, right? So this one shows that definitely the density of this graph here is greater than the other one. Now what does this density actually tell us, and how is it useful? So there have been a research conducted on some Broadway musical industries. So Broadway musicals are different groups. So it's like some companies. This research was conducted by someone. He was named Ryan Uzi. So what he did was he did a survey on these musical companies, and what he was looking at. So assume that you are planning to open up a music industry, and now for this musical company you need some people. So you are going to consult some of your friends to come and participate here with you. Now the friends which you are choosing here, they might know each other or might not know each other. We don't know. So whenever you are forming here a musical company, you have some people. Let's say these are the people which I chose for creating my company. Someone will be a director here, someone will be a manager here, someone will have some other post. Now these people will be having a network between them. So in some cases it is so possible that all these people which I have chosen, they already know, each of them knows each other. In that case I say that this network is very dense, all these people know each other beforehand. In another case, another case can be, so this one is the case where I'm talking about. Let's say I chose 10 people and all these 10 people, they most of them know each other. Another case can be the people I picked, they do not know each other at all. So nobody knows no one else. So here there is a lot of communication between the people because they know each other. In this case here, the people don't know each other. It will take them some time to get to know each other, and initially the communication will be quite less. This one is an average situation here. The people which I am choosing, some of them know each other beforehand, some of them don't know each other. And what he looked at is, if you look at this plot here, on the x-axis you have the density of a network. So this is in percentage here. So density of a network, it can be between 0 to 1 because we have normalized it. So the minimum number of edges in a graph can be 0 and maximum number can be n choose 2. We are dividing it with n choose 2. So the range of this density here is from 0 to 1. So this is the density on the right hand side. On the and on the on the y axis he had the success rate. So there were different metrics which he used to compute success rate. Might be the monetary benefit these musical companies made. So if you look at the graph here, what is happening? If you have a very low density where people don't know each other, or if you have a very high density that people know each other heavily, in both the cases the company was a flop. And you and the company was a success in those cases where the density was around an average. So this is a very basic network measure which have been used in conducting a research like this. Okay. Uh, let's talk about the next measure. So when I'm looking at a graph, so the graph which Satvik showed us, the graph looked quite dense to me. There were a lot of connections. Might not so happen in some other networks, we don't know. So another thing we can look at is the connectedness of a graph. Now, how do you define connectedness? So connectedness can comprise a lot of measures. So what comes to your mind when I say about, okay, look at the connectedness of a graph. So connectedness is a very vague term. Can you try to be a bit more specific and tell me when I say about connectedness, what comes to your mind? What all things can we look at in connectedness?
uh, how frequently each other are connected, basically. If you look in a graph, how nodes are connected to each other.
Come again.
Uh, in a graph, we can say how each and every node is connected.
How each and every node is connected. Okay, in what sense? Like, what is its degree? Is it?
Um, um,
Let me write it down. How connected each node is. We can use some measures for that. Okay. You can think of everything you studied in graph theory. So think about everything which comes to your mind: spanning tree, discussed algorithm, min cut, max cut, anything. By the way, I don't think there is something as max cut. Distance between each node to every other node. Yes, that's a very nice measure, quite an advanced one. We'll discuss about it. So I take each node and I compute its distance from every other node in the network. So let's say I have this graph here. I take vertex 1, compute its distance from vertex 2, vertex 3, vertex 4. Same I do for vertex 2 here, so on and so forth. I do this. And maybe then I take an average of some kind, a very good measure. Okay, anything else? So the very first thing when I say about connectedness is whether a graph is connected or not, right? Whether this graph has connected components. So most of the time when you look at these networks, so in our case, the network was a very small one. So when you extract some of those online data sets which we looked at, you might end up getting a network like this here, a very nicely visualized network. So what do you observe here when I talk about connectedness? You see this one giant component here sitting in the center of this network, this one over here. And other than this giant component, we have these small components, most of which are just isolated nodes and maybe nodes having a chain of 2 or 3 here, like it's a chain of 5 here. Actually, when you visualize something like a Facebook or a Twitter graph, it will look something like this. So these all are the people who probably made an account but have not added any friends as of now. Somebody might have made a network and might have added a few friends who are not connected to the remaining network, right? But most of us will lie somewhere here. So people who have been frequently using Facebook for the last 1 or 2 years would lie somewhere in this big dense part over here. So this component, this property of real world networks, we call it the existence of a giant component in the network. Most of the time, whenever you extract any real world network, it will look to you like this. There will be this large number of small components and a big giant component will be sitting at the center. Whenever we analyze these graphs, most of the time we leave out these small components and restrict our study to this one big giant component over here. Okay, coming to what Navneet was saying, taking turn towards that. That's actually a very nice thing which is called 6 degrees of separation. Has somebody heard about it? What is 6 degrees of separation? You might have had instances in your life when you meet someone and then you would realize after some time that you know that person, he is a friend of a friend or something like that. I think it would have happened to almost all of us. So, for an example, when I was in BTech, the receptionist which was there in our institute, after a few days, I came to know that she was my brother's friend's mom. And I'm sure each of us would have encountered experiences like that. And then we sort of think that it is a coincidence, but actually, such things they are not coincidence. They are the way in which our real world networks are wired. So we call that 6 degrees of separation. In that term, so very nice experiment was conducted by a scientist named Stanley Milgram. The experiment went something like this. So what Milgram did was he chose some subjects in different parts of the world, and so we have these different subjects here. Let me just write it down. So we had a large number of subjects. These were the participants of our experiment. What these participants had to do was Milgram chose a professor in USA, and what he did was, what these people had to do, he gave a letter to each of these people. So each of these participants, they were given a letter here. The letter had few, this letter consisted of a few basic information about this professor, like the name of the professor, his institution, and his address also. So now assume you were a participant in this experiment. I gave you this letter which had this name, institute and address of a person, of a professor in USA which you probably won't know. What you had to do was, you had to somehow make this letter reach that professor. And in order to do this, you cannot directly send this letter to the professor. So although his address is written in the letter, you can't just post it to that address. What you are supposed to do is, you can only pass this letter to someone whom you know well. So they call it, you can pass this letter to someone whom you know on a first name basis. That actually means, when we say you know someone on a first name basis, means you are that close to that person that you can call them by their first name. Something like they are your buddy. So you can pass this person to any of the other person whom you know very well. And then that person will also sort of repeat the same thing. And in this way, you have to make this letter reach this professor here. So if you know the professor directly, then you can go and hand over this letter to him. Otherwise, you can hand it to someone whom you know well, and then they are expected to pass it to someone whom they know well, so on and so forth. And what Milgram tried to trace was whether these letters finally reach this target person or not. And if they reach this target person, in how many hosts do they reach? So how many people become the part of this experiment in between? So do you have any guesses here? How many hosts do you think which this letter will reach this target node here? The answer is written right at the title of this slide. So on an average, this number is 6, which is actually pretty less looking at the population of the world. So when this experiment was done, it was seen that although the success rate of the experiment was very low, its success rate was 30%. That is 70% of the letters were lost midway because people wouldn't have that much time. Some of the people wouldn't have forwarded it. But out of these 30% letters which reached the professor, most of them reached the professor in a median of 6 steps. So that's why we call it 6 degrees of separation, which says that you are connected to anyone else in this world within an average of 6 steps. So most of us can actually reach anyone else in this world in just 6 steps if we follow the right path. The problem is we do not know the path. Okay. Now comes to how can I see it in a network. So let's say I'm given a network and I want to figure out what is the degree of separation in this network. I want to quantify this thing. How can you do that? So the very first thing is you can look at the diameter of a network. Do you know what diameter is? We also call diameter, you might have heard about it. We call it the longest shortest path. Now, what is this longest shortest path? Is it the longest or the shortest? Can someone explain this? What is this longest shortest path? So diameter means that in a network, if you look at the nodes which are the most distant from each other, then what is that distance? So basically you figure out the shortest path between every pair of nodes. So for every UV pair, you figure out what is the shortest path between them, which we call the distance between the nodes. So you figure out this distance. So maybe for some two nodes it is 3, for some node it is 6, for some it is 7, for some it is 8, and then you choose the longest one from here, the maximum one from here, which is 8. So you can say that it is the maximum of distance between UV where U comma V belongs to E. That is our diameter. But what we are essentially doing here in when we figure out this average shortest path, that is again a similar procedure. Instead of looking at the diameter, I figure out the shortest path between every two pair of nodes. Same like this is 3, 6, 7, 8, so on and so forth, and I take an average of this. So that tells me on an average how connected the people in this network are. And next I'm going to actually show you a network. So during the Milgram's time when he conducted this experiment, this value was 6. But if you tried, someone did an experiment to figure it out. So it was from Facebook research to figure out what this value is for Facebook. And for Facebook, this value all the more shrinks to 3.5. Which means that you are connected to, on an average, you are connected to almost every person on the Facebook within a maximum of 4 hops. So everyone in the Facebook, you can find them by looking at your friends is friends is friends is friend. That's all. So this Facebook network is this small, you can say. What you are seeing in this figure here is on the x-axis. So now this is not a number here. Here what you see is a plot. What is this plot here? What I'm going to do is, I'm going to look at the first user on the Facebook, exactly like Navneet said. Next, I'm going to look at the distance of this user from every other user on Facebook. So from some users it will have a distance of 1, from some others it might have a distance of 5, 6, so on and so forth. And you take the average of this. So maybe the average distance of this user from other users come out to be 2.5. For some people it will come out to be 2.9. So you can say it's a node characteristic. So for me, it will give me on an average how distant I am from these people on Facebook. For Navneet, it will give me on an average how distant is Navneet from all the people on Facebook. For Shagufta, it will give such a value. And it will do this for every user on Facebook. And next, what you are seeing in this plot is on the x-axis, you have the different possible values of this average degree. And on the y-axis, you have the number of people who are having that average degree. So what it shows you is there are very little people over here. So if you see this value here is in millions. So there are very, very little people here who have this average distance as 2.7. That is, they are very close to every person in Facebook. Within just 3 hops, they can reach everyone else. There are few other people for whom this average distance is 4.7. So on an average, they are 5 steps away from everyone else in the Facebook network. But on majorly, if you look at the mean of this network, so the mean of this network is actually 3.57. So if we look at an average person on Facebook, he can reach to almost everyone else in 4 hops. So that is what it tells you. Average shortest path length. Okay. Uh, Coming to the next property, transitivity. Can someone try to guess what is transitivity? You would have heard of transitive relations in discrete maths. What are transitive relations? What is a transitive relation? Can someone tell me? Everyone should be able to answer this question. Okay, Shagufta says if a node is connected to, if a node A is connected to B and B is connected to C, then A would be connected to C. Perfect. And that's also the definition for your transitive relations. So transitive relations say that assume I have a relation here where A is related to B and B is related to C, then A must be related to C. So if I have a relation where I only have A, B, C and not AC, I say that this relation is non-transitive. In the case of social networks, what we are doing is we are taking this one step ahead. So first let's understand it in terms of relation. So given a relation, I won't say that this relation is transitive or this relation is not transitive. What I'll tell you is the degree of transitivity of this relationship, how transitive it is. So let's say I have AB, then I have a BC and I have an AC. Then let's say I have an AEEF, but I do not have a EF here. So I say that the transitivity of this, so by your discrete mass definition, this relation is not transitive because it doesn't have AF. But I, on the other hand, will say, okay, this relation is half transitive because for AB and BC, it has AC, but for AE and AEF, it doesn't have AF. So it's not that it is not at all transitive. It maintains this condition of transitivity here, but doesn't have it here. So I say the degree of transitivity is half, and then I do the same thing in a network. So I simply look at all such kinds of pairs and see how many of them are closed. That is, I have this thing also here. Let's actually do it. So say I'm given a network which is something like this, and I want to figure out how transitive this network is. So a very simple network here. So what I'm going to see here, what I'm going to look at here is you can actually convert it in a relation also. So the pairs which I have is I have X, Y, uh, and then I have Y, Z, and then I also have an X, Z here, right? So this means in this particular case I have a transitivity here. So what we do in social network is we say if I see any such kind of a structure, this kind of a structure, I say it is a triad. A is connected to B and A is connected to C, but B is not connected to C. So I say it's a triad. And if I have something like this, I say it's a triangle or it's a closed triad. Transitivity tells me what fraction of these triads are triangles. So let's figure out what are the triads here. So if you see here, so XYZ is a triangle, but it's a closed triad, right? So I currently mark it like this. Later on, I'll see whether it's closed or not. So this is one triad here. So now I'm referring this as open triad and closed triad. Let me say it's an open triad. It's a closed triad. I'll figure out how many triads are there and then we'll see how many of them are closed. So this is one triad here. X is connected to Y, X is connected to Z. Then I have this one over here, 2. Then I have this one over here, 3. Then I have what? This one over here, ZX and ZW. It's also again a triad. Then I have this ZW and ZY. This is again a triad. So in a total, I have 5 triads. Is any other triad possible? I think these are the ones. So these are 5. And next you see how many of these 5 are closed. So X is connected to Y, X is connected to Z, Y is connected to Z. So this one is closed here. This one is also closed. This one is also closed. This one is not closed because I don't have an edge here, right? So this one is an open triad, and this one also here is an open triad. So out of these, 3 are closed, 2 are open. So I write down the closed one here. So you get this value to be 0.6. Any doubt here? Okay. Um, I think we are up on time. We did cover very less today. What we are going to discuss tomorrow is about, so this was one way of looking at transitivity in a network, which is at the network level. So you see what fraction of these triads are closed. Tomorrow we'll try to look at this phenomenon more at a local level. So try to think, what do I mean when I say that I'm looking at it in a local level. So I'm going to each individual node. So right now I looked at the entire network and I computed it. So how many of these are closed? Next, what we'll do, we'll go to each individual node, compute some transitive, transitivity value for each individual node and then average them. So think about how that can be done, what comes to your mind. We'll discuss more about it tomorrow. So this thing over here, it is called transitivity, or you can also call it, it's also known as global clustering sometimes. Cluster is what? Cluster is when things connect to each other and make a cluster. Right? So this is here called global clustering. So how much your network is clustered when you look at it globally. Tomorrow we'll look at local clustering. Okay, if you have any doubts, you can stay back and ask the, I think I'm done.
Thank you, ma'am.
Welcome.